Amphoteric and polyprotic substances. We've seen poly before. Where did we see it? Polyatomics, right? Meaning what? More than one. Okay? So a polyprotic substance is a chemical that has the ability to lose or gain more than one proton or hydrogen ion. It only does it one step at a time. And let's look at carbonic acid. So here we start off with H2CO3. If you had no idea what carbonic acid was, how could you figure that out? Look on page 8. Okay? There's all the acids that we're going to work with are going to be there. And if they're not there, it'll tell you what it's called. Carbonic acid is, how many hydrogens does it have? 2. So carbonic acid is what we call diprotic. It has 2 hydrogen ions that it can donate. Doesn't mean that it will. It has the ability to. So in the first, what we call the first ionization, because that's what happens when you ionize it. We put it into water. We're going to lose 1 hydrogen, or we're going to donate 1 hydrogen. And the water will accept it. Okay? In the second step, we're going to start with this compound. We're going to start with bicarbonate, HCO3 minus. It's going to donate the hydrogen, so we're going to left with CO3 2 minus. Every time we lose a proton, we have more electrons than protons, so our charge will go up. Notice that we start here at a net charge of 0. We donate a proton, now we have a net negative charge. We donate another proton, we have a net negative charge of 2 minus.
So would you have a net charge of H3O2 plus?
Nope, because what happens is in our big old beaker of water, we have H2CO3 ions happening. We have water molecules. And this will donate 1 hydrogen, so now we have H3O plus ions, but we still have water molecules in here, and we have HCO3 ions now floating around. This guy will donate. We're going to get some more hydronium ions. No, I can't make it go into focus. There we go. Okay, so you start with carbonic acid, you throw it into water. That's what's floating around in here. We have H2CO3s floating around in here. This is a weak acid, so it's going to donate 1 hydrogen, and so we get HCO3 minus floating around in there, and we have hydronium ions floating around in there. But we also have water ions still floating around in here. This is going to donate a hydrogen, so we're going to get another hydronium ion, and then we're going to have some carbonate ions floating around in here. Eventually, what will happen is it will hit its equilibrium point, and it will just kind of like float there in an equal kind of amount. But at the very beginning, as I have my beaker of water and I add carbonic acid, initially there's going to be lots of water molecules and a couple of bicarbonates. And then as I keep adding it in, there's going to start being some carbonates, some bicarbonates, some carbonic acids, lots of hydronium ions, and still some water ions. Okay? You asked. I'm just going to bring this down a bit. Okay. Some organic acids have several hydrogen atoms in the molecule, but not all the hydrogen atoms will be acidic or acidic hydrogen ions. Acidic hydrogen ions are simply the hydrogen ions that can be lost in an acid or base reaction. In an organic acid, the acidic hydrogens are the ones that are attached in the COOH group. Yeah, so we learned this, CH3COOH. This functional group means that this is a carboxylic acid, right? It's this hydrogen that gets donated. This one here that's attached to the carbon, the three that are attached to the carbon, right? Here C, C, double bonded O, OH, 1, 2, 3, H, H, H. It's all coming back to haunt you now, isn't it? Okay? These hydrogens here stay with that carbon. It's this hydrogen on this alcohol group that gets donated. So when you write it out, you get CH3COO negative. So let's look at it. Here's a polyprotic. Meaning that it can, polyprotic means that you can donate more than one hydrogen. These are the hydrogens that can be donated. There's two acidic hydrogens. Okay? No, not this one. We can't take those ones. Okay? Another one, C3H5O COOH twice. No, sorry, 3 times. It's this hydrogen here. It's that hydrogen there, and there's 3 of them. Right? Because there's 3 of these carboxylic acid groups on there. Not polyprotic, meaning that it does not have more than one acidic hydrogen to donate. It only will donate this hydrogen here. These ones here, we can't touch those. Okay? It's only at the end, on the end. Polyprotic bases, there aren't a whole lot of them, but there's a couple. They usually have a negative charge that's less than 1 and can gain more than 1 hydrogen ion. So, the most common ones are sulfate and phosphate. Phosphate has a net charge of what? 3 minus. Okay? Plus water. This, and it's same thing. It only happens one step at a time. This will gain 1 hydrogen. What's going to happen to my charge if I add a positive to it? going to go just to 1 negative. And then I have an OH negative. Then this guy here, we come back down. We can gain, look, we have a negative charge. We can gain a proton. So this is going to donate. I'm now going to have 2 hydrogens. What happens to my charge if I take 1 proton off and this is 1 negative? It's going to be neutral and it's going to be 0. And I have a hydroxide ion. How do we know what? Because here we already have the hydrogens. And it's already at a 0. So it's not going to go, other than ammonia, it's not going to gain hydrogens when it's already balanced. Yeah, that's your best indicator. Now, ammonia is the exception to the rule. It will take on that hydrogen and it will create ammonium ion. Okay? All right. Let's look at these reactions here. NH3 plus water gives us NH4 plus and a base. Stapled my notes backwards. That's awesome. Physics 20, I stapled them completely out of order. That was really good too. Okay, if this gained hydrogen, what does that say about ammonia? Yeah, what does it make this? A base. That makes this the conjugate acid. Water is going to lose the hydrogen or donate the hydrogen, makes this the acid, and this the conjugate base. Here, when I look at hydrochloric acid reacting with water, I get a hydronium ion and a chloride ion. What happens to the hydrochloric acid? It donated it, which means that it's the proton, or it is donated the proton. It's the acid. Water became the base. Hydronium ion is the conjugate acid, and chloride ion is the conjugate base. So don't ever get in your brain that hydroxide ion can be the only base indicator. Okay? What do we know about this process here? What can we compare between the two? The which, Riley? Yeah, we could look at the partners. What's common between the two reactions? Water is in both reactions. In the first one, okay, so in the first reaction, water is an acid. In the second reaction, water is a, okay. This means then that water can have 2 roles. And when one substance can be either the base or the acid, that means it's amphoteric. It's like an amphibian. It's like a frog. It can live on land. It can live in water. It can be both. Ambidextrous, yeah, you can be left-handed and you can be right-handed. Okay, let's look. There's 2 reactions in here. When we look at the first reaction, HSO4 2 minus does what? It gained, which makes it a in the second reaction, HSO4 minus does what? It donates the proton, which makes it the acid. Because it can play either the base or the acid, HSO4 minus is amphoteric. It can go to H2SO4, it can go down to SO4 2 minus. Okay? Most amphoteric substances will contain at least one acidic hydrogen. So HSO4 minus, HCO3 minus, H2PO4 minus. They can go up. They can go to H3PO4 and become phosphoric acid. They can go down to HPO4, become phosphorus acid. HCO3 minus can go up into carbonic acid, or it can go down into carbonate, or carbonate ion. What am I saying wrong? Why does that seem weird? Carbonate ion. I don't know. Just haven't seen it for a while, I guess. Okay? Not all amphoteric substances fall into this category. Look at water. Water can act as an acid and form hydroxide, or water can act as a base and form hydronium ion. NH3 can act as a base and form ammonium ion, or it can act as NH2 minus. Look and see on page 8 and 9 if the chemical is found on both sides of the table. So here, water is amphoteric because it's found here at the very bottom here and at the very top up here. Okay? If we find HSO4, here's HSO4 right here, and it's over here somewhere. That's HSO3. That's sulfite. It should be H2SO4. Oh, right here. That's what you're talking about. Sorry. Okay, it's on both sides of the table. Here's H2PO4 minus, and here's down here is H2PO4 minus. So if they're on both sides, then they're amphoteric. If they're not, then they're not amphoteric. Okay? That's it. That's amphoteric and polyprotic in a nutshell.